In this lecture, I am going to present what are the step-by-step procedure of stiffness matrix method for the analysis of continuous beam. Then I would like to solve one problem based on the 3-span continuous beam with both ends are fixed and sinking of one support. These are the different steps which is followed for the analysis of continuous beam by stiffness matrix method or displacement method. So in this method, first determine the degree of kinematic indeterminacy, that is degree of freedom. Then identify the independent displacement components. Then assign the coordinate directions in the independent displacement components. Then prevent all the independent displacement components to obtain the restraint structure. Then determine the forces developed at the coordinates in the restraint structure due to the loads other than those acting at the coordinates. Then determine the stiffness matrix K by giving unit displacement to the restraint structure in each of the coordinate direction and find the forces developed in all the coordinates. Then compute the final forces in the coordinate direction. So this is denoted by P. Then according to the stiffness matrix method, so this is the equation. P is equal to P dash plus P delta. So P is the final forces in the coordinate direction and P dash is the forces due to the external loading and K is the stiffness matrix and delta is the displacement matrix. So this is the column matrix and this is the K is the square matrix, P is the column matrix. So P is equal to P dash plus P delta. Then P is equal to P dash plus K into delta. Then by using the condition of equilibrium of forces to compute the displacement in the coordinate directions. So delta is equal to K inverse P minus P dash. Then after knowing the displacements, compute the internal member forces by using slope deflection method. Then coming to one problem, analyze the continuous beam shown in figure. If the support B sinks by 10 mm, use displacement method, take EI is equal to 6000 kilonewton meter square. So this is the 3-span continuous beam ABCD. End A is fixed and end D is fixed, and B and C is the intermediate support, and the span length AB is given 3 meter, BC is 4 meter and CD is 4 meter. The moment of inertia of span AB is 2I, BC is 2.5I and CD is 2.5I. So this is the continuous beam, but here there is no loading on the span AB, on the span BC and on the span CD. But the settlement of the support B takes place by 10 mm. So this is the support B. So the settlement of the support B takes place by 10 mm. So this is given. So first you have to find out the degree of freedom. So here the rotational displacement takes place at the support B and support C, because here at the support A there is no displacement and at support B there is no vertical displacement, only the rotational displacement takes place here at B. Similarly at C there is no vertical displacement, only the rotational displacement takes place at C. The unknown displacements in this problem are the rotation at B and rotation at C. Hence the coordinates selected at B and C are as shown in figure 2. So here assign one coordinate at B and assign another coordinate at C. So this is the forces required at the coordinates in the restraint structure due to load. This is the fully restrained structure with assigned coordinates. So here the coordinate this is 1 and this is the coordinate 2. So here the settlement takes place 10 mm at the support B, and this is the direction of piston moments developed. First you take the resistance structure, that is, take all supports are fixed and find out the piston moments due to external loading or due to the sinking of support. But in this problem there is no external loading, only the sinking of support takes place at the support B. So you have to find out the piston moments only due to the sinking of support. So first find out the piston moments. So due to the sinking of support B, so here MFAB and MFBA, only due to sinking of support B. So find out the piston moment MFAB and MFBA and MFBC and MFCB. But MFCD and MFDC is 0. Here there is no effect due to the sinking of support. So here the moment is 0. MFCD is equal to MFDC, this is equal to 0. So here find out due to the sinking of support what is the piston moment MFAB, MFBA, MFBC and MFCB. So you know how to find out the piston moments due to the sinking of support. So the formula, this is minus 6EI delta by L square. So this is the formula. So using this formula minus 6EI delta by L square, so you can find out what is the piston moment due to sinking of support. So here given the length of this is 3 meter and the delta is given 10 mm. So take 0.01 meter and the moment of inertia of AB is given 2I. So here find out the piston moment MFAB. MFAB is equal to minus 6E into 2I into 0.01 by 3 square. So this is equal to minus 80 kilonewton meter. Then MFBA is equal to minus 6E into 2I into 0.01 by 3 square is equal to minus 80 kilonewton meter. So here this is the negative moment due to the sinking of support B, and for span BC, so here the moment is the piston moment on the span BC due to the sinking of support B is positive. So here MFBC is equal to 6C into 2.5I into 0.01 by 4 square. So this is equal to 56.25 kilonewton meter, and MFCB is equal to 6C into 2.5I into 0.01 by 4 square. So this is equal to 56.25 kilonewton meter. So for span BC this is positive and for span AB this is negative. The piston moment due to the sinking of support. And MFCD and MFDC this is equal to 0. Then after getting the piston moments, then find out the forces developed in the coordinate direction due to given loads. So here P1 dash is equal to MFBA plus MFBC and P2 dash is equal to MFCB. So find out P1 dash MFBA plus MFBC, but you know MFBA is equal to minus 80 kilonewton meter and MFBC is equal to 56.25 kilonewton meter. Then after simplification, this is equal to P1 dash is equal to minus 23.75 kilonewton meter. Then P2 dash is equal to MFCB, this is equal to plus 56.25 kilonewton meter. These are the forces due to the external load. There is no force in the coordinate direction 1 and 2, so the final force is 0. There is no forces acting at the coordinate 1 and 2, so the final forces P is equal to P1, P2, that is equal to 0, 0. P1 is equal to 0 and P2 is equal to 0. But the forces due to the sinking of support, here you got P1 dash is equal to minus 23.75 kilonewton meter and P2 dash is equal to 56.25 kilonewton meter. So here you take the force due to the sinking of support P dash is equal to P1 dash, P2 dash is equal to minus 23.75, 56.25. So these are the final force and this is the force due to the sinking of support. Then determine the stiffness matrix. Then determine the stiffness matrix by giving unit displacement to the resistance structure in each of the coordinate direction and find the forces developed in all the coordinate directions. So here this is the restraint structure with unit displacement in coordinate direction 1. So here you take the end A is fixed, end C is fixed and end D is fixed. Only you have to give the unit displacement at the coordinate 1. This is the unit displacement, theta is equal to 1. So apply unit displacement in coordinate direction 1. 1 radiant rotation is given to support B in coordinate direction 1. Then find out the forces developed in the coordinate direction 1 and 2 using the slope deflection equation. First apply the unit displacement at coordinate 1, theta is equal to 1, and find out what is the force developed at the coordinate 1 due to unit displacement at the coordinate 1. Similarly, what is the force developed at the coordinate 2 due to unit displacement at the coordinate 1, K11 and K21 find out. So K11 that you can find out using the slope deflection equation. So for K11 you have to find out from this span and from this span. So from this span you have to find out the K11 from span AB. So this is 4EI theta B by L plus 2EI theta A by L, and from this span, so K11 is equal to 4EI theta B by L plus 2EI theta C by L. So this is the equation K11. For AB span the I value is given 2I, and for BC span the I value is given 2.5I. So here you take 4E into 2I theta B by 3 plus 2E into 2I theta A by 3 plus 4E into 2.5I theta B by 4 plus 2E into 2.5I theta C by 4. But you know the end condition. So theta A is equal to 0, theta C is equal to 0 and theta B is equal to 1. Theta A is equal to 0, theta C is equal to, theta B is equal to 1. So this is the end conditions. Then after putting the end condition in this expression, so this is the expression, then put theta B is equal to 1, then K11 is equal to 5.167 EI. Similarly find out K21. So for K21, this is K21. So here you take the slope deflection equation 4EI theta C by L plus 2EI theta B by L. But the I value is given 2.5I and the length is given 4 meter. 4E into 2.5I theta C by 4 plus 2E into 2.5I theta B by 4. Then after putting these end conditions, so K21 is equal to 5 EI by 4 is equal to 1.25 EI. Then apply unit displacement in coordinate direction 2. So in this case, so here you take the support A is fixed, support B is fixed, support D is fixed, and apply unit displacement in coordinate direction 2. So this is the restraint structure with unit displacement in coordinate direction 2. So here 1 radiant rotation is also given to support C in coordinate direction 2. Then find out the forces developed in the coordinate direction 1 and 2 by using the slope deflection equation. So here also find out, so due to the unit displacement at coordinate 2, so find out what is the force developed at coordinate 1 and what is the force developed at coordinate 2. So K12 is the force developed at coordinate 1 due to unit displacement at coordinate 2, and K22 is the force developed at coordinate 2 due to unit displacement at coordinate 2. So K12 is equal to 4EI theta B by L plus 2EI theta C by L. This is K12 is equal to 4EI theta B by L, 4E into 2.5I theta B by 4 plus 2E into 2.5I theta C by 4. In this case, theta B is equal to 0, theta D is equal to 0 and theta C is equal to 1. So put these end conditions here in this expression. So K12 is equal to 1.25 EI. Then find out K22. So for K22 you have to find out from this span and from this span. Apply slope deflection equation to the span BC and to the span CD. So from this span, so K22 is equal to, from the span BC, K22 is equal to 4 EI theta C by L plus 2 EI theta B by L, and from the span CD, K22 is equal to 4 EI theta C by L plus 2 EI theta D by L. This is. Then apply the end conditions here. So K22 is equal to 5 EI. So here you got the stiffness coefficient K11 and K12, K21 and K22. These four stiffness coefficients become the stiffness matrix. So here you got K11 and K21 by using the unit displacement at coordinate 1, and you got K12 and K22 by using the unit displacement at coordinate 2. Then this is the final forces acting in the coordinate direction 1 and 2. P is equal to 0, 0, and the stiffness equation is P is equal to P dash plus K into delta. This is the stiffness equation, you know, P is equal to P dash plus K into delta. Then K delta is equal to P minus P dash, but you know the stiffness matrix K is equal to, this is K11 and this is K12, this is K21 and this is K22. So K11 you got 5.167 EI, and K12 you got 1.25 EI, and K21 got 1.25 EI, and K22 you got 5 EI. So this is the stiffness matrix, and this is the displacement matrix, the column matrix, and this is the force, the final forces which is acting at the coordinate 0, 0, and this is the force due to the sinking of support, because here there is no external loading, and here you got the forces due to the sinking of support, P1 dash and P2 dash. Then after simplification of this expression, and by taking EI common here, EI 5.167, 1.25, 1.25, 5, and this is the displacement matrix delta 1, delta 2 is equal to the force matrix 23.75 minus 56.25. Then delta 1, delta 2 is equal to, this is the expression. This expression is the inverse of the stiffness matrix, and this is the force matrix. Then after simplification of the inverse of the stiffness matrix and the force matrix, after multiplication of the inverse of the stiffness matrix and the force matrix, and finally you get the displacement matrix delta 1 and delta 2. So delta 1 is equal to 7.79 by EI, delta 2 is equal to minus 13.198 by EI. So here the displacement at the coordinate 1, delta 1 is equal to theta B is equal to 7.79 by EI, and displacement at the coordinate 2, delta 2 is equal to theta C is equal to minus 13.198 by EI. At the ends A and D are fixed, theta A is equal to theta D is equal to 0. Then after getting this displacement, then you can find out what is the final moments. So MAB is equal to, so here you find out the moments. So this is the beam. So find out the final moment MAB, MBA, MBC, MCB, then MCD and MDC. You know the fixed end moments MFAP. So the final moment MAB is equal to MFAP plus 4 EI theta A by L plus 2 EI theta B by L. Similarly, MBA is equal to MFBA plus 4 EI theta B by L plus 2 EI theta A by L. Then MBC is equal to MFBC plus 4 EI theta B by L plus 2 EI theta C by L. Then MCB is equal to MFCB plus 4 EI theta C by L plus 2 EI theta B by L. Then MCD is equal to MFCD plus 4 EI theta C by L plus 2 EI theta D by L. Then MDC is equal to MFDC plus 4 EI theta D by L plus 2 EI theta C by L. The final moment MAB, MFAB plus 4E into 2I theta A by 3 plus 2E into 2I theta B by 3. After putting the value of theta A and theta B in this expression, so finally the moment MAB is equal to minus 69.613 kilonewton meter. Similarly, find out MBA. MBA is equal to MFBA plus 4E into 2I theta B by 3 plus 2E into 2I theta A by 3. Then after putting the value of theta B and theta A in this expression, MBA is equal to minus 59.227 kilonewton meter. Then MBC is equal to MFBC plus 4E into 2.5I theta B by 4 plus 2E into 2.5I theta C by 4. Then after putting the value of theta B and theta C, MBC is equal to 59.227 kilonewton meter. MCB is equal to MFCB plus 4E into 2.5I theta C by 4 plus 2E into 2.5I theta B by 4. Then put the value of theta C and theta B here. Then the final MCB is equal to 32.995 kilonewton meter. Then MCD is equal to MFCD plus 4E into 2.5I theta C by 4 plus 2E into 2.5I theta D by 4. Then after putting the value of theta C and theta D here, MCD is equal to minus 32.995 kilonewton meter. Then MTC is equal to MFDC plus 2E into 2.5I theta C by 4 plus 4E into 2.5I theta D by 4. Then after putting the value of theta C and theta D, MDC is equal to minus 16.497 kilonewton meter. So these are the summary of final moments. MAB minus 69.613 kilonewton meter, MBA minus 59.227 kilonewton meter, MBC 59.227 kilonewton meter, MCB 32.995 kilonewton meter, MCD minus 32.995 kilonewton meter, MDC minus 16.497 kilonewton meter. So these are the support moments, but you can check at support B or at support C, the net moment should be 0. So here you see, so at support B, MBA plus MBC is 0, and at support C, the net MCB plus MCD is equal to 0. So this is the direction of the moment. So here you got MAB is equal to minus 69.613 kilonewton meter. So for negative moment, apply the direction anti-clockwise, and here MBA is equal to minus 59.227 kilonewton meter. So here also you got negative. So for negative moment, apply anti-clockwise direction, and MBC 59.227 kilonewton meter positive. So for positive moment, apply the direction clockwise, and MCB 32.995 kilonewton meter. So here the direction is clockwise, and MCD minus 32.995 kilonewton meter. Here the direction is anti-clockwise, and MDC is equal to minus 16.497 kilonewton meter. So here also the direction is anti-clockwise. So these are the direction of moments, and after knowing the direction of moments, then you can draw the bending moment diagram. This is all about the analysis of continuous beam when both ends are fixed and due to the sinking of one support. Now all are clear how to analyze the continuous beam by stiffness matrix method when both ends are fixed and sinking of one support.